Hello, can anybody hear me? Am I audible? Can anyone see the video? I guess the video and audio are fine, so I will be starting with the presentation right now. Hello, I am Devi Bakul from the binary exploitation team, and I will be taking today's binary exploitation training session for day one. So what do we do in binary exploitation? We exploit software for fun and profit. And by exploiting, you can cut out that word and add it as hacking instead. So, yes, we are hackers. So, in this session, I will be covering what binary exploitation is, why vulnerabilities exist, and how hackers can take control of programs. So, I'll be starting with the basic introduction now. So, what is binary? Does anyone know what binary is? Like, if you have any idea on what it is, you can put it in the chat. Okay, so binary is basically is a compiled program that runs on your computer. So programs are often written in languages. You might be familiar with some of them, like C and C++. But when compiled, they turn into binary machine code. A binary is the final executable result of the compilation process. The machine code consists of opcodes, and the central processing unit, or CPU, executes directly on these codes. This direct execution gives binaries their speed, but it also has a drawback. It means that it lacks the safety nets provided by managed routines. At this stage, there is no human readable code. So exploitation works by manipulating memory, CPU registers, and program behavior. This is how the compilation process occurs from the source code, the code that you write, to the executable code. First, the source code is run by the preprocessor, and the preprocessor converts it into the preprocessed code, which is basically just a lengthier, more advanced version of your source code. Then this pre-processed code is taken by the compiler and converted to an assembly code. Then the assembly code is taken by the assembler and converted to the object code. And via the linker, the object code is converted to the final executable code. We have a we have a tool in our terminal called GCC. And what GCC does is it does this entire process of compilation in a single step. So we can convert our source code, which is text.c, to our executable code, test, using this command, gcc test.c with the flag O, and then test. If you want to see details on this test file of yours, you can do file test. Then you will see an output on your terminal which looks somewhat like this. It tells you that it is an ELF 64-bit LSB pi executable x86-64 version numbers and stuff like that. And it might be a bit hard to understand at first. So I'll just explain what a pi executable is. So basically, they are just mitigations provided by the GCC compiler while compiling your code so that it is a bit harder for hackers like us to break into the binary. Now, what is exploitation? So first question, what is binary exploitation? Imagine a program is running on your computer. Normally, it follows rules. It takes input, processes it, and exits. But if the program has a bug, an attacker can abuse that bug and make the program do something it was never supposed to do in the first place, like spawn a shell, read secret files, or crash. That act of abusing compiled programs using vulnerabilities is called binary exploitation. So here is a small snippet of code that I have over here, which demonstrates such a vulnerability. This is a C code, and in here, there is a function called gets, which has this vulnerability. So we have a buffer which can store 40 characters. But the issue with gets, which is used to read the input from the user, is that it can take more than 40 characters from the user. But let me explain the C program in a little bit more detail. So first we have hash include stdio.h. So this is a header file, and stdio is used to interact with the console. It will allow you to enter the input into the console and get the output back from it. So stdio stands for standard input and output. It's kind of similar to the import functions and libraries that you have in Python. If any of you are familiar with Python, then we have our function. So we have int main over here. Main is the name of the function. A function is just a block of code which executes when you run that function. Main is necessary for the program to run. Basically, what the int over here does is that it will determine what value the program or the function in this case will return. So if you put int, it just says that an integer will be returned by the function after its completion. So back to gets. Gets allows us to enter more than 40 characters. There is no limit to the number of characters that you can give as an input for buffer. It will for gets. So what happens here is that you can go past the limit of 40, and that will cause unintended behaviors in your program. Here, what printf does it just prints whatever you give within the quotation marks to the display. %s is used to print the contents in the buffer. Now, why do these vulnerabilities exist? There are two main reasons why. First reason is blind trust. Some of the programs often trust user input too much without validating it. A good example of this is our prog.c file. So what happens here is that the programmer trusts that the user will not input values which have more than 39 or 40 characters. So thus far, do you guys have any doubts? I'll wait for one more minute to check if you guys have any doubts. Please put your doubts in the chat. I assume that the first slide is clear then. I'll continue with the second slide. So, other than blind trust, there are other issues as well. Those are unsafe functions. There are functions like gets, string copy or strcpy and printf, which have a few vulnerabilities in them, and these vulnerabilities can be exploited. Gets can be used to overwrite stuff in the program memory. strcpy or string copy has the same issue as well. And printf can be used to both overwrite as well as leak memory. So, why do we exploit binaries? Say you're writing a code and you want to know whether your code is secure or not. Then, if we know a little bit about binary exploitation, then we can identify vulnerabilities in our code. We can also make the binary do whatever we want. And in case we find a vulnerability in someone else's code, then we can notify them about these vulnerabilities and hence result in a safer software. There are also a lot of bug bounties that are happening, and they are very rewarding. Big companies like Google, Microsoft, and Cisco pay large sums of money for reporting these kind of bugs and vulnerabilities in their products. All right, so how are these binaries run on our computer? So when you double click a program or run it from the terminal, the operating system, which could differ from your device, it could be Windows, Linux, or Mac OS. The operating system steps in first. So what the operating system does is that it first transfers control to the loader, and this loader loads the binary into memory. The loader takes the binary file and places it into the computer's RAM, which is like the computer's memory, so that the CPU can access it quickly. Then the loader gets related library files. Like most programs depend on helper codes that already exist, like printf to print text or malloc to allocate memory. These live in things called shared libraries. The loader finds them and connects them to the binary. Then the loader transfers control to the binary. Once everything is ready, binary is in memory and libraries are linked, the loader steps aside and says it's all yours and hands execution to the binary. And from this point on, the CPU starts executing the binary's instructions line by line. And this is the moment where vulnerabilities, memory bugs, and exploits come into play, because now the program is alive in memory and we can interact with it. And if you want to execute your executable file, you can just put dot and hyphen, no, dot and slash, and then give the name of it, and it will execute the binary for you. So, libraries are binaries that exist within the system to aid in returning your program and providing useful functions, but it is not run as such as a program. So, a few library functions that have been used in this program ABC are printf and gets. Printf is used to print stuff to the terminal, and gets is used to get input from the terminal. As I mentioned before in the previous slides, gets has an issue. It will let you take how much ever give how much ever input as you like, which can exceed your buffer limits. So, in order to prevent such casualties, there are different safer alternatives for gets, like formatted gets or fgets. Similar functions are also present for printf, like fprintf and sprintf. Does anyone have any doubts till the content I've covered so far? Is everything clear? If you have any doubts, you can mention it in the chat. I'll wait for like one more minute for a doubt, and if there are no doubts, I will just assume that all the doubts are cleared. Also, I forgot to mention this. For bug bounties, there is a popular bug bounty happening around, and that is pawn to own. The thing about pawn to own is that in pawn to own, you will be provided with many different varieties of devices, and if if you can find any sort of vulnerability in these devices, you can take them back with you along with a huge cash prize. There was once a Tesla last year which got hacked, and the hacker was able to take it back with him. So, yeah, things like these do exist. You have to explore options like these, and that is why binary exploitation is a really, really useful field. So, yeah, since I did not hear any doubts, I'll just continue with libraries as such, or aka shared libraries. So you can think of libraries like an actual physical library of books. So in programming, these books are usual or useful functions that solve common problems. Instead of writing complex code to interact with the graphics card to print text, you can simply borrow the printer function from the standard C library, which is glibc. This allows developers to focus on unique logic rather than commonly used logic or hardware details. So, a few examples of these so called books are printf, scanf, and fputs. They are functions. Okay, so you might have heard a word over here, dynamic. So, yes, there are dynamic libraries as well as static libraries. So, what dynamic libraries do, they are like binaries which are linked in runtime. So, what happens in these sort of binaries is that in the binary as such, during compilation, there is just a reference to the actual library. So, the content in the binary is not physically present in the binary as such. So what happens during runtime is that whenever you call a function from in the binary that is connected to the library, it goes to the reference and it does a few mathematical calculations, and from there it finally gets the actual address of the library which contains that function. So it then directly jumps to that address and it stores that address somewhere in your binary or program. So that is it for dynamically linked binaries. But once you use that function, then you don't have to repeatedly do that mathematical calculation in order to get that address. That address is stored in tables. But for statically linked binaries, they are directly linked during the compilation process and not during runtime. And dynamically linked binaries are much safer than statically linked binaries. I hope dynamic and statically linked binaries and such sort of libraries are clear for you. If you have any doubts, you can put them in the chat. Moving on to why we need shared libraries. The first reason is abstraction. We don't need to know how a function works in order for it to do what it needs to do. Like for printf, we know that printf prints things in the terminal, but we don't need to necessarily know the inner workings of printf or how printf is able to print these things in the terminal in order to use it. So that is one key point. And the other key point is that it reduces redundancy. Say you have to print a lot of things in the terminal, but at different intervals. We don't need to have a copy of printf in our system or in our binary every single time in order to print it. If we have it stored in a separate file, we can just call it whenever we need it. We don't have to repeatedly put it in every single binary file that requires it. And this is a very good example of it. Say I have three programs, program 1, program 2, and program 3. Now, program 1 wants to get input from the terminal. So it is requesting for scanf, while program 2 needs to print stuff to the terminal. So it's requesting for printf. And program 3 also needs to take input from the terminal, but only as a string. So in these cases, what happens here is that all of these functions, printf, scanf, and gets, are all stored in the library libc. So in case program 2 wants to switch from displaying output to getting output, it does not need to implement the gets function in it. It can just request for the gets function from the library. So it decreases the workload on the programmer. But then we have a major question. How do libraries get the work done? Like how is printf able to print contents on the terminal? It is done via syscalls. Syscalls have been mentioned in the reversing session, but I will take them once again as a refresher. Okay. The syscall basically calls the kernel to request a service. It's how the program asks the operating system to do something that it can't do on its own. For example, say you want to read a file or write to the screen or create a process or just access the network. Think of it like a service request. The OS performs a task safely and then returns a result back to the program. There are a lot of functions underlying. Like, say you have printf. Printf calls the write syscall to put text onto the screen. So printf is just like a wrapper to the write syscall. Similarly, gets is a wrapper to the read syscall. Now I'll give you a few examples of such syscalls. This is a syscall table for x86-64 architecture. So from here you can get all the system calls that you'll require. This is the read syscall and this is the write syscall. Okay, so back to the presentation. We might all have the doubt. Can we call syscalls without having to go through a library function? Like, can we call the kernel directly? Uh, yes, we have a doubt. Could you? Oh, okay, sorry. I'll increase the mic volume from next time. I'll keep that in mind. Okay, so can you hear me now? Is it clear? Is the volume still low? Okay. I think that it is okay from our side. Please try to increase the mic volume, speaker volume, sorry, from your side. I think someone already says that the mic volume is a bit better. Okay, since it's clear, I will be continuing with the presentation. All right. So we have an instruction in assembly. Do you remember when I mentioned assembly over here? Yes. Our pre-processed code gets compiled to assembly code. So assembly code is essentially just a low level language. It is somewhere in between our binary code and our high level language code like C, C++, or Python. So each instruction in an assembly corresponds to a particular instruction or task in binary, but it's still human readable. And in case people have any difficulty with, like if any of you guys have difficulty in understanding the assembly code that I will be showing you in the next slide, I can explain it in brief. But if you still face more difficulties, it would be best if you could revisit the reversing training session that we had yesterday and the day before. It is mentioned in detail in the reversing session. Okay, now I will be moving on with the assembly syscall instruction. So over here, I will be working with x86-64 architecture. So an architecture is just the way in which the CPU processes the instructions and data, and X32 processors process data in 32-bit chunks, while X64 processes the data in 62-bit chunks. There is also MIPS as well as ARM architectures as well, but I will mostly be concentrating on x86-64 assembly and the architecture. So in this architecture, arguments for the syscalls are passed via specific registers. As you can see here, the first argument is loaded into the register called RDI. The second argument is loaded into the RSI register. The third argument is loaded into the RDX register. And as you can see over here, a value is being stored into RAX. So what is this value? It is the syscall number. The syscall number basically lets us or the kernel basically lets the kernel know what syscall you want it to do. So basically what service you want it to execute. And here over here OX3B is for the EXCV syscall. You can look into it in detail in the syscalls page, syscalls.dev page. So the syscall, if you look at syscalls or syscall RDI, RSI, RDX, the last one line, it looks very similar to how functions give their arguments. But it's not the same. It's just similar. So now I'll be moving on to stack, which is how the program manages memory. So stack is a part of the program's memory, and it is used to keep track of functions and their local data. So it is used to track the control flow of these functions. So it works like a bottom to top pile of plates or boxes, like how you would stack CDs on top of each other or books on top of each other, which means that you can only add to the top of the stack and you can only remove from the top of the stack as well. Usually we call putting or adding values to the top of the stack as pushing those values to the stack, and removing values from the top of the stack as popping values from the stack. The push and pop instructions in assembly work in the same way. Now I'll move on to the call instruction. The call instruction is an instruction that pushes the address of the caller function, and then the corresponding return instruction returns to the previous procedure. Now, if you look at the call instruction, it is made up of, or it comprises of, two smaller and simpler instructions. So, the call instruction comprises of a push RDI instruction and a jump to the function instruction. And the return instruction just pops the return address, which points to the next instruction that we are supposed to execute from the stack, and then just jumps to it. So now you might all have a doubt. Why is stack a target? And one of the main reasons are is because of the fact that local variables or variables that you define in your function, if you don't explicitly give it as static or global, those variables are stored on the stack itself. So what happens here is that since they're stored in the stack, we can overflow a function's local variables, and we can use it to reach or even override the return address. And if we override the return address, the program does not know where to go next. So we can basically change the program's control flow. In von Neumann architecture, code and data share the same memory. The stack stores the user input or buffers right next to the control data. So, and the stack grows downwards from the higher address to the lower address, while the values in the buffer go from the move upward from the lower to the higher. So basically, if you input a lot of characters into the buffer, you can basically go past RBP and into the return address. By corrupting the return address, an attacker controls the return instruction. Instead of returning to main, the program jumps to an address of the attacker's choosing, which could be shellcode or rope gadgets. Other than local variables, there are many different types. Like there are global variables, there are static variables, there are also register variables. Now that I've taken the stack session, do you guys have any doubts on like how the stack works? Or I will go into detail on how the stack works in the later slide, but until now, does anyone have any doubts? Like on the call instruction or the ret instruction? Or if you have any doubts on any of the assembly instructions mentioned here, you can ask that in the chat. Okay, moving on. Before the demo, I would like to mention or explain how the function stack frame works. So a program like every time a C function runs, the program creates a small space on the top of the stack for it, and this is called the stack frame. A stack frame is basically just a frame that contains data for the function in the stack. So say you first execute a function, namely the main function. So the stack frame of the main function goes here. And in the main function, suppose you call a function f1. Then what happens is that the stack frame for f1 gets pushed into the stack on top of the main stack frame. And if f1 recursively calls itself again, then that gets pushed on top and it builds up like that. And suppose this is the last function you're calling and that function returns something. Then what happens is that once this function completes its execution, it gets popped out of the stack. and then execution resumes to the next instruction in the function. And then once it's completed, that also gets popped out of the stack. And then finally, it goes back to main. And once the main function finishes its execution, that too gets popped out of the stack. Oh, my bad. And after the main function executes, the instructions are all done via the operating system. Like the operating system does its own instructions in order to exit from the program. But before it goes to main, it first executes start or underscore start. That's a function. And in the underscore start function, it executes libc start main. And within the libc start main, it executes the libc start call main function, which has main as one of its arguments, and this function calls the main. So once main finishes its execution, it goes to the instruction right below the call main instruction in libc start call main. Now I'll go in detail about the stack frame. Okay, suppose we call a function. Let's say call main, but with some arguments. So first what it does is that, as I said before, call can be subdivided into two simpler instructions. One of them is push RIP, which pushes the current saved RIP into the stack. So this will have the saved RIP. And then after that, what it does is it jumps into the function, and it's from here that the function prolog starts. In function prolog, the first instruction that it does is that it does push RBP. So the RBP, or the base pointer of our previous function, like the function that called this function, gets pushed onto the stack. And then and once this gets pushed onto the stack, the RSP points to the old RBP, like in this position in the stack. So what we do is that we move the value, or move whatever RSP is pointing to the RBP. So the RBP also points to the same place. I'll put this in red. Red denotes the RBP and black denotes the RSP. And after this, we just use the instruction sub RSP with the amount of space that you need to store all of your local variables and parameters, basically to extend the stack. So after this extension, since the RSP points to the top of the stack, the RSP moves over to here. Then what happens is that now we've got our stack frame. And this is the stack frame that we will be using for the function. We can put things there. But once the function is over, we have to destroy the stack frame. So in order to destroy the stack frame, we have to do the opposite of what we did till now, which means that we have to bring the RSP back to where the RBP is pointing. So for that, we use the instruction move RSP, comma RBP, which moves the RSP back to where the RBP was pointing. So we can destroy this. And once that's over, we need to restore the old stack frame of the function that called this function. So for that, we need to move the value of RBP. You have to put the value of RBP to the value that it had previously. So for that, we use pop RBP. So now the RBP's value is the same as the old RBP. The RBP points somewhere, I guess, below. And then what it does is we use the ret instruction, which basically does pop RIP. So the saved return address or is taken by the RIP register, and execution continues as follows. The return instruction just basically jumps to the top of the stack, which is basically the RIP. Now I'll be moving on with the demo. Hello? Yeah. Uh, I will be moving on with the demo, but before that, I will be looking forward to doubts if you have any. So if you have any doubts regarding the stack frame or how the stack works or how the function prologue and epilogue works, you can mention that now. While I'll wait for your doubts to be asked and cleared, I would like to share something. Like we will be having InCTF calls on 13th of December, and the finals will be around the second week of January. In order to get updates and to join the community, you should join our Discord server. Also, there are demo challenges in Traboda. You can access them by going to our site, to the InCTF Junior site. And from our website, you have to just register to the you just have to register for the CTF competition, and from there you'll get a few sample mock questions that you can attempt in order to get familiar with the CTF and how challenges work in CTFs. This is the website, and you can click here, register now. That is just because it isn't HTTPS yet. You just have to give your username or email and the password if you are already logged in. Otherwise, you can register with your email and then you can put your name, and from there you can get started. And once you get started, a few mock challenges will be prepared in the same format as the actual CTF, so you can get familiar with it more. And in case you have any doubts in the challenges, you can always open a ticket and ask any one of us conducting the CTF via the ticket service in Discord. Now we'll be moving on with the demo. So the first demo I will be showing you is of, one second. I don't need to put it in presentation mode, my bad. The first demo I'll be showing will be of buffer overflow. So in buffer overflow, we're just basically using gets in order to to write past the RIP. So this is our code, our vulnerable code. It's the same code as what I showed to you before. It takes in, uh, it has a buffer that has a size of 10. So it can take in 10 characters or 10 bytes, since each character is 1 byte. And you're getting the values for this buffer via the gets function, which can take more than 10 bytes. Feel free to ask any doubts in this code if you have any, like on what percentage s is, or what printf might be, or what void over here does. Okay, assuming that there aren't any doubts, I'll be moving on with the demonstration. Okay, we can use GDB, a tool, to go through the decompilation or the assembly code, basically, in order to step in through each of the instructions and get to know in detail what happens behind the scenes in these sort of programs. It's used as a debugger to debug our program. We can use spawn debug in order to um, debug it even more efficiently, because once we say we start the program, it shows us all the registers that you will require, and it will also show us all of the assembly code in the executable file. It also lets us step in through all of the functions, examine each of the function and each of the instruction, and then it will also show us everything that is there in the stack at that present stack frame. But in case you don't have pawn debug, you can use the hook function, which basically lets you define whatever you need. Say you have, we'll use hook start for it to hook stop, sorry, for it to activate in every single step in instruction. Say you want to like display something, print, let's say, all of the registers. Then you can just put info registers, and then click end. So next time, every single time you step in, let me decrease the size a bit. sorry. Yeah. Um, my scroll was not working for a bit. I apologize. But it will show you the every single information of each and every registers, both in hexadecimal format and in decimal format. So in case you are not able to use Spawn debug, or you don't want to use Spawn debug and want to interact with vanilla GDB as it is, you can use hooks to like, or you can define hooks to make your life a bit more simpler. So I'll continue with this. First, we use the gets function to get input from the stack. From the user. And what it does here is that it takes whatever input that you give it via the terminal and puts it into the stack into this memory location or address. Say I give a huge value like a lot of A's. So as you can see, like in the stack, I'm using the tell command over here. Or if you are using vanilla GDB, you can use x slash gx $RSP in order to go through each of the values in the stack. And as you can see, all of them are overwritten by A, which in hex represents is 0x61. So now we'll continue with it as usual. We'll print it. And then when we go to the return address over here is not something that you'll usually see. It's overwritten with all of the A's. So it causes a segmentation fault, which means you can't go much further in the program. So instead of all of these A's, you can put an actual address over there, which is what we're using in red to win, in order to exploit the program and to change the control flow. So if you want to install Pawn debug, you can just do pip install Pawn debug and you can install it in your own system. Okay, I'll show you a red to win demo right now. So let me show you the challenge. So in the red to win challenge will look a little bit like this. So what we have over here, you don't have to look much into in detail about set vbuff over here. What I've basically done over here is that I have disabled buffering for both std out and std error. So we're calling a vulnerable program which has a buffer which can take in 64 bytes or 64 characters. But since we're using gets, we can go much larger than that. So we can use this to call our win function, which will give us system access via system binsh. System binsh will basically give you access to the terminal in which the program is running in. Okay, so I'll go into GDB. So let me start into it. This is just the buffering. Now we're going into the vulnerable program. Use S to step into it. If you use N, you will go past the call. It will just run the call and go to the next instruction main. So we'll use S. Continue. So this is the vulnerable function. Oh, this is one of the vulnerable functions that we have called gets, which will let you take in as much input as you need. And as for win, we can disassemble win using this command called disass bin, or you can just put disassemble as well, that also works. And this is the vulnerable function. So we need to keep an idea on what, like we need to have the address with us in order to exploit. So I'll just keep the address with me for now. So let's give a lot of A's, but just a few A's and then a few numbers as well. It does not detect anything. Why would that be the case? Let's disassemble through the vulnerable function. Vulnerable. As you can see here, it takes the value in RBP minus OX40 and puts that in RAX. Then what it does is it takes this RAX, puts it in RDI, sets EAX to 0, and then calls gets. So from here, RDI, which is the first argument that gets is going to take, which will be a buffer, is basically RBP minus 0x40. Like that's where it is stored. And since the return address is right below the RBP, we need to overwrite (72 bytes) or we need to input 72 characters in order to reach the return function. And after that, we just have to input the address of the function that you want to execute, which is our win function. So, one second. This is win. Just keep a copy of this. In order to make the scripting easier, we can use pawn tools, basically pawn tools. So it will also give us a template which you can access via pawn template. Okay, that's nice. So I'll just copy all of this, create a new script. We have to change our path to challenge, like our challenge path. And since I will be running this, you don't have to do this, but since I will be running this in the terminal, a different terminal, in tmux actually, I can set up the terminal using context.terminal. Tmux. I'm splitting it vertically, so I'll put split W minus, sorry, flag, it's just a flag. And here we can specify our GDB script. Right now I'm not specifying anything. Now sorry, there was a small issue. I copied the template and I forgot about it. This is the challenge file. We'll do context dot terminal equal to tmux. You can use I functions to check all the functions that you have in your program. I'll get win from here. So this is our win function right now. And as we know, like as I've shown you before, we have to overwrite 72 bytes. So let's say this is our payload is equal to, you can put any character you want here. We'll put a padding of 72 and then we'll add win to it. P64 is used to pack 8 bytes, basically as bytes. All right, now let's send this to the program. So how do we send it to the program? We can use io dot send line and then payload. Yes, that's it. Now let's run it. We can, I'll have to go to tmux for this. We can do python 3 script.py and put gdb as the argument. Red to win was successful, but there was a small issue over here. If you can see here, it shows us that it is not aligned to 16 bytes. There are two ways in which you can resolve this error. Let me take the disassembly of win. You can, instead of starting from over here or here, just start from over here, over this instruction, because it's just that the stack is not aligned to 16 bytes, and it's because it's creating a new stack frame over here. So it's creating a new stack frame over here and it's moving the base pointer around, which is why it is not getting aligned. We can also use ret, and that will be covered more in the next day training session under ROP chains. So let's go back to our win function. See, now even it shows detached from process. Now let's check what it does. Let's see ls. It shows you whatever is there in in your file right now, like wherever you are currently, like the directory. That's how you hijack into the program in order to get the flag. You can use that to exploit or to go and make changes in their own system. Basically, you'll get full access of that system. So let's go back to the PPT. So why does binary exploitation matter? It teaches you how software breaks and how attackers think, how real world exploits work, and how to write safer code. So it makes you a stronger security engineer or developer. So in case you are creating a program, it's better to know how the program can go wrong so that you can so that nothing goes wrong in the after the production process. So binary exploitation is really important in the cybersecurity field. And that's it for today's session. If you guys have any doubts, you can still ask them. GDP has a documentation that you can use. There are also multiple cheat sheets as cheat sheets as well. Sorry. You can also refer to BIOS wiki to know more about buffer overflow, stack overflow, and also about ROP chains and such. And if you want to know more about the different flags that are there for GCC, then we can refer to the like you can refer to the man page of GCC. Like for the Red to Win challenge, I used FNO stack protector, and also I used NoPy as well. NoPy, as I've showed you NoPy in like Pi in the beginning, like in the second slide. So what Pi basically does is that it randomizes the address in every execution. So the thing that I did for Red to Win, where I just copy pasted the address, that will not work for Pi. We'll have to find it dynamically. Yeah, you can just type in BIOS wiki or wiki.bios.in. Over here, you can get an entire roadmap on how to learn. You can go with stack, overflow, integer overflow. There are multiple vulnerabilities that you can exploit. Does anyone have any more doubts from any part of the presentation or the training session? We'll wind up the session if anyone doesn't have any more doubts. Okay, we'll be winding up the session now. Bye. Done, right? Most of the people there were my family.